this video, Columbia University's doctoral candidate, Rashidul Berry, will teach Newton's.
I'm very excited today. I'm very excited because we're gonna solve friction problem today by using Newton's second law. I often tell people that if human beings lose everything from this world except Newton's second law, we lose nothing, because we can rebuild everything using this equation. So this equation is very powerful. We're going to use this powerful equation to solve loss of friction problem. But more importantly, I'm going to give you a full understanding of friction. So let's dive into physics. So friction can be written as like this, and we can divide it in three parts: static friction, kinetic friction, and we can call it just in general. So this one when the object at rest, kinetic friction when object in motion. When object in motion, we say it's a kinetic friction. When object in motion. This is a general case. This is a general case. Now, let me write the coefficient of friction. So, coefficient. So, coefficient of static friction is mu, s. This is a Greek letter, and this is called mu, and s for static, mu k. And for general case, it's just mu. So what would be the equation for static friction? It would be Fs is equal to mu s Fn. Why Fn? It's because Sir Isaac Newton said that the friction is proportional to the normal force. Very important. So I really want you to pay attention to this. So force, so the friction, let me erase this again. So friction, why normal force is because why friction is because force of friction is proportional to normal force. Let me highlight it. It's very important. All right. So let's go back to our conversation. This is in the future, I'm going to help you understand why this is less than or equal to. But we're going to keep as it is now. We're going to call it Fs is equal to mu s Fn. We're going to fix this equation. We're going to come back to this equation and we're going to fix this equation. All right, now this one would be mu k, the force of kinetic friction is mu k Fn. And this is a general case. Ff is equal to mu Fn. All right, few things you need to know is that static friction is always bigger than kinetic friction, and mu is always Ff over Fn, and Fn is always greater than Ff, making the mu always less than 1. and the unit for mu is nothing. There is no unit for mu. Why is that? Because this is force and this is force, so Newton cancel with the Newton, so the mu does not have any unit, and mu is always less than 1. Okay, so with this understanding, hopefully we can now create some problem. Let's create a problem. Let's say Mr. Berry, let's create a problem. This is a rod. I can draw it better. There is a rod and there is a box on the rod, and the box is 10 kilogram. Now Mr. Berry wants to move this box, and he wants to move this box by a car. So he attaches a rope between the car and the box. So he tie a rope. Alright, now he will apply different forces. So he will apply different forces. So let's create a table. Let's say applied force gonna be changed. So the applied force would be he gonna apply 0 Newton, and then 10 Newton, and then 20 Newton, and then 38 Newton, and then finally 40 Newton to move the box. Okay, so now we're going to create a table, very important table. So this is going to be the scenario. So scenario, this is going to be applied force, this is going to be force of friction, this is going to be type of the force, whether it is non-static or whether it is kinetic. This is going to be net force, this is going to be acceleration, this is going to be how many forces acting on it. So let me how many forces acting on the box, and what law is it? Newton's first law or Newton's second law? Okay, so so let's see now scenario number 1. Let's apply 0 Newton. If I do apply 0 Newton, what is the force of friction? 0. Is it a static friction or kinetic friction? Static friction. This is kinetic. What is the net force? 0. What is the acceleration? 0. How many forces acting on it? 2. Newton's first law or second law? So Newton's first law. Let's understand this one by creating a force body diagram for scenario number 1. For scenario 1, we're going to create a force body diagram. So how many forces acting on it? 2. So one is the weight. Weight is, if mass is 10 kilogram, the weight has to be 98 Newton. And the normal force is also 98 Newton. So let's see whether it matches with the table. So this is scenario 1 and this is the free body diagram for scenario 1. Let's see whether it matches with the scenario 1. Scenario 1 said net force is 0. Yes, net force is 0 right here. Why net force is 0? Because both arrows are equal in magnitude but opposite in direction. They cancel each other. So the net force is 0. So net force is 0. Okay, now we're going to do scenario 2. Scenario 2, we have 10 Newton. So now Mr. Bari decided to pull this ball, pull the box using 10 Newton coming from the car. All right, now applied force is now 10 Newton. What's the force of friction? So now the box will increase its friction to 10 to keep it at rest. Why? Because Newton's first law. The first part of Newton's first law said object at rest like to stay at rest. So the box try to stay at rest. This box will do everything possible to stay at rest. Everything possible. That includes increasing the friction to 10 Newton so the box can stay at rest. So the applied force would cancel the force of friction, so the box would still be at rest. So the force of friction is 10. So now is this static or kinetic? The box is still at rest. So is of course static. The net force is 0 because box not moving. Acceleration is 0. How many force acting on it? 4 forces acting on it. And what Newton law? Newton's first law. Alright, now let's see scenario 2 over here. Why 4 force acting on it? Maybe you don't see why 4 force. So the box, we have the weight. Weight is the same, 98 Newton. And the normal force, which is the same, 98 Newton. So 2 forces acting at the y direction. Now we have a 2 force acting at the x direction. Let's make it smaller. This is F applied and this is F friction. So this one is equal in magnitude to this one, so net force at the x direction is 0. This one is equal in magnitude to this one, so net force at the y direction is 0, and that's exactly what we wrote. We wrote that how many forces? We wrote 4 forces, so 4. Acceleration is 0 because there is no net force, and it is static because this box is still at rest. So let's highlight it. Okay, excellent. Now we're going to do scenario 3. So we're done with scenario 2. We want to do scenario 3. Scenario 3 is 20 Newton. Okay, scenario 3 is 20 Newton. Okay. Now you probably want to ask, what is the minimum force you need to move the box? So let's ask this question, because you don't want to trial. Mr. Bari, what is Mr. Bari is doing is trial and error. He first applies 0 Newton, the box doesn't move. He applied 10 Newton, the box said, I'm not going to move, because since you apply 10 Newton, I'm going to apply also 10 Newton opposite in direction. Cancel each other. So I will be stay at rest. But Mr. Bari need to move it, and the box doesn't want to move it. Now Mr. Bari want to know, instead of trial and error, what is the minimum force he need to apply so that he knows the box would move. Let's see. So the question is, let me clean this up. So the question is, minimum force, minimum applied force, needed to move this box. You know that 0 Newton fails, 10 Newton also fails. Now he about to apply 20 Newton. Okay, 20 Newton. You see, let's he gonna do one more trial and error. Let's see what happened. 20 Newton. That's scenario 3. So 20 Newton. So the friction, the box is gonna say, you are applying 20 Newton. You are pulling the box now to 10. Now it's 20 Newton. So I'm gonna apply equal amount of force, but on the opposite direction. So I call it force of friction, because force of friction always opposite to the to the applied force. All right. That means this is static because the car is at rest. Now, net force is 0. Acceleration is 0 because net force is 0. How many forces acting on it? 4. And Newton's first law. Now, let's draw a force body diagram, free body diagram for that scenario. Scenario 3. So let's draw the box. So let's draw the box. We have, at the y direction, we have equal in magnitude, so net force is 0 at the y direction. At the x direction, you have F applied and F friction. This is equal in magnitude but opposite in direction. Notice that this arrow is longer. I have to make sure that they are equal in magnitude. So they has to be equal in magnitude. So this one and this one equal in magnitude but opposite in direction. So how many forces? So this is 10 Newton, this is 20 Newton. That's why this is bigger. All right. So let's highlight them. Okay, so let's highlight them. All right, now you're going to do scenario number 4. So let's do scenario number 4.
Did you read this?
No, I don't.
Yeah.
Hold on, let me.
What are you teaching right now?
Go. I'm teaching. Close the door. So scenario 4. Mr. Body is forced to go to scenario 4 because he badly wants to move this car. So now instead of 20, he is doing push. He's applying 38 Newton. Okay, 38 Newton. It's kind of a trial and error. So the question we raise over here is minimum applied force need to move this box. Now Mr. Barry badly want to know that, because 0 Newton fails, 10 Newton fails, 20 Newton fails. Now he is about to do 38 Newton. But he needs to know, this is kind of a wasting time. So instead of wasting time, he wants to know what is the minimum force he need to apply so that the box is moving. So what he do? He uses this equation. This will give him the minimum force needed to move this box. Or another way, this will give him the maximum static friction of the box. Alright, maximum static friction. If he applies a little bit more than maximum static friction, then the box will be moving. So Fs is, so the maximum static friction of the box is mu s Fn, and mu s is given in this problem. So I'll give you the mu s. I told you that mu s is always greater than mu k. So mu s is 4, let's say, and mu k is 0.3. All right. So 0.4 times 98 Newton, so it's going to be 39.2. So this is the maximum static friction. So the maximum static friction is 39.2. If you apply 39.2, then if you apply more than 39.2, so if you do apply 39.1 Newton, if you do apply 39.1 Newton, the car, let's say this is 39.1 Newton, 39.1 Newton. The car will increase its friction to 39.1 Newton, and it's still going to be at rest, and it's still net force going to be 0, it's still acceleration going to be 0, and it's still how many forces acting on it is 4, and it's still Newton's first law. Why is that? It's because 39 is smaller than 39.2. To move the cart, to make sure that the cart, the box, give up the inertia, you have to apply 39.2. Anything less than that, the box can increase its friction to the same magnitude, so it cancel out, so the box at rest. What about 39.2? 39.2. If you apply 39.2, then the box would be in constant motion. And acceleration would be 0 because net force is 0. If you apply more than 39.2, let's say 40 Newton, then box would be accelerating. Because net force is going to be more than 0. So that's what we're going to explore now. With 38, let's change this to 39.1, not 38, 39.1. I already put that, 39.1, and 39.1 is not enough as we see that. So 39.1. So let's draw a force body diagram for 39.1. Alright, so 39.1, that should be 4. Still at the y direction, nothing is going on. See, this is bigger than this one, is because this is the magnitude is 39.1, and this magnitude is also 39.1. Alright, so now that takes us to the last scenario, scenario number 5. But before we do that, I want to highlight that. Okay, so now I'm going to go back to table and to see scenario 5. Scenario 5, you apply 40 Newton. 40 Newton. Okay, is 40 greater than 39.2? Yes, 40 is greater than 39.2. So the box will start accelerating. So then what is the force of friction? Alright, to understand that, we have to go back right here. What is the maximum kinetic friction of this box? That is mu k Fn. So mu k is 0.3 and Fn is 98 Newton, and that gives you 29.4. So So that will give you 29.4. I'm going to highlight it is because it's get crowded. 29.4 Newton. All right. So now the object will be motion. Since the object will be motion, the force of friction is 29.4 Newton. Is it static or kinetic? It's kinetic because the box is moving. All right, now we're going to find the net force. So let's find the net force. Now, let's see how can we find the net force. Let's draw the force body diagram. Let's draw the force body diagram right here. This is for scenario number 5. Now, this is Fn and this is Fg. Nothing is going on at the y direction. This is Fa and this is Ff. See, Ff is now smaller than Fa. That means there is a net force. So net force is, what did I tell you net force? Net force is Ma. So let's see, net force is Ma. Net force is Ma. All the forces. All right, so what are all the forces? All the forces acting on this box, all the forces is Fa minus Ff is equal to F net, because Ma you can replace by F net. So applied force is 40 Newton and force of friction is 29.4, so 10.6. So the net force is 10.6. So this is 40 Newton. This is 29.4. So F net is 10.6 to the Newton to the east. All right, so we're gonna write 10.6. So what is the acceleration? Acceleration again, Newton's second law. F net. So F net is 10.6 Newton and mass is 10 kilogram. So acceleration is 1.06 meter per second square. So acceleration of this box is 1.06. Not the best place. Acceleration is 1.06 meter per second square to the east. Why to the east? Because if the net force is to the east, acceleration is to the east as well. Net force is always at the direction of acceleration, and acceleration is always at the direction of net force. Now we're going to color code this one, the whole thing, this one with this one. So we found along the way we found the acceleration. So you're going to write acceleration 1.06. And how many forces acting on it? 4 forces acting on it, as you see. 1, 2, 3, 4. And Newton's second law, this one. Why Newton's second law? Because net force is more than 0. In fact, net force is way more than 0. All right, now the last thing we're going to do the friction diagram. So to do the friction diagram, I'm going to do it here. You're going to call it x-axis. This is our x and this is our y. Okay, so let's draw it. So this is our x and this is our y. So what is our x? Our x is Fa. and our y is ff. Okay, so let's put some value. 10, 20, 30, 40, 50 and 60. 10, 20, 30, 40. Alright, so now we're going to draw the point. So the first point is 0, 0. The second point is 10, 10. The third point is 20, 20. The next point is 39.1, 39.1. The next point is 40, 29.4. So 40, 29.4 right here. Alright, so let's connect the dot. And let's connect the dot. Okay, so let's see what's going on. So this one is fs less than or equal to mu s fn. So you're going to fix this equation that I wrote before in a second. This one is fk is mu k fn, and this one is called maximum friction, maximum static friction. So let's write now Newton first law and Newton second law. So this is Newton first law. This one is what do you call inertia. This is box at rest, and this is the Newton second law, or this can be Newton if the velocity is constant. Okay, so now let's write what is the minimum static friction. Minimum static friction 0 Newton at right here 0, 0. Maximum static friction 39.2 Newton, and that is right here. Minimum kinetic friction 29.4 right here, and maximum static friction kinetic friction maximum is also 29.4. How do you know? Even if you increase your applied force to, let's say, 70 and 80, if you double your applied force, this is 40 Newton and you have 29.4. If you double your applied force, the force of friction is still 29.4. Thank you for watching. This video was made possible by Brilliant.